very well structured and documented. Like the documentation is very good. So the recipes is part of the tidy models, and I think let's try to just load up tidy models. And you might not have it installed, so maybe because you gotta but this is good. You can install it, and then I'm gonna just talk a little bit about the bigger picture of doing standardizations and normalizations. So let's just take a big step. Oh yeah, wow, you're already done? That was so fast.
Yeah.
Okay.
It's because I think I already have installed it, but I updated my R like 2 days ago or something. So maybe that's why. I don't know.
Maybe. Oh, well, it's already done. So
yeah.
But anyway, I think.
But you can still talk.
Yes, exactly. Yeah. Just taking a big step back. These things that we do to data, we do them because we're going to be running some statistical tests, or we're going to be doing some statistical modeling of some type. And each of those, I don't know how much you all know about this, but I'm just going to talk as if you don't. So I hope that's okay. And so each of these tests all have slightly different assumptions about what the data looks like and how they work with data. So, and the way that you can sometimes sort of fit arrange your data to be able to fit these assumptions is by doing some processing to the data beforehand. So some pre-processing. And the thing is, the way that tidy models handles this is quite nice. It's got a really nice framework. But the thing is that you want to do these transformations for each individual for that specific test. So you want to be doing you don't want to be processing your data and then using that data for everything. You only want to be processing the data right before putting it into the model. Now, sometimes some models or some statistical tests have similar assumptions and require similar changes to the data, but not always. So within the tidy models, you can be able to apply those transformations and changes to the data right before it enters into running the statistical test. And that's kind of exactly what you want to be doing. So like a really good example of this is to drop missing values. Most statistical tests rely on the assumption of there being no missing values. And so like just within R, for instance, if you have, hello.
Hello.
We just got started, so you're good.
Thank you.
So right now I'm just explaining the big picture right now. So what I was saying is, one example is missing values. So linear models, linear regressions, they in R, when you give the data into the linear regression, what it'll do is it'll automatically drop, or I think you have to actually set an option within the thing, within the model. I can't remember, but anyway, so like it'll either throw a warning if there's missing values, or you can just drop everything in the missing values. But the thing is, you only want to drop the stuff that's necessary for the model, and you only want to drop the stuff right before the data enters the model. That's because like if you do other statistical tests, or if you do other things, like if you want to calculate the mean of each of your columns, you don't want to drop all the missing from the data sets. You want to be able to only drop what's necessary. So the tidy models is a really nice like framework for doing statistical tests because it allows you to be able to move that processing right before it enters into the model. And the other thing is that certain processing happens to certain variables and not to others. And this really depends on what their role is in the statistical test. So if you're running a linear model, there's going to be some confounding variables on top of there being like a variable that you're actually interested in. And so you don't want to necessarily be doing certain processing on the variable that you're interested in versus the confounding variables. So you can do specific types of transformations based on processing based on that. So what I'm going to cover a little bit today is, so there's a ton of different ways of processing your data before it enters into the statistical test, and I'm the most common ones are transformations and normalizations, and that's what I'm going to be covering right now. Inside of the recipes, inside of the recipes website. So Cecilia, if you can create just a comment here, just so that, so comment and then recipes.tidymodels.org. So that's the website for the recipes package. And inside of the reference list, there is a section for transformations that has like them listed there. If you want to like look more into that, this is definitely the first place that you should go, or also the getting started section of the recipes website. So the thing is, and this gets when I was like kind of thinking about how to talk about this session, is that transformations, the type of transformations. So there's a lot of different types of transformations that you can do, and there's sort of different types of like related normalizations that you can do, and they all really, really heavily depend on what statistical test you're doing and what your research question is, and what you want the interpretation or like the way that you interpret the results to be. And it also really depends on some basic checks for the assumptions of the statistical tests that you run and what they tell you. Now both of these are like, you could probably fill like a whole 3-hour session on these, and they get quite mathematical very quickly. I'm not going to get into any of that. What I'm going to do is just say I'm going to assume that you already know you've already learned some of the mathematical reasons for why you would choose certain transformations and why you don't, and also why you're choosing certain transformations based on your research question. And I'm just going to talk about how to transform your data. So I'm not going to get into the math details, because I think that's way outside of the scope of this session, and it would take forever. So even though we're going to be covering the recipes package, which works best within the tidy models framework, I'm going to be adding a couple of ending prep things so that you can use whatever we do in the recipes, whatever we do here from the recipes package, to be able to use it in any other way that you might use run statistical tests. Because learning the tidy models framework does take a little bit of extra time. It's a really powerful framework, but it does take some extra time. So I'm going to do some add some small things at the very end of our pipe to be able to say, that you can use the transformations anywhere. Okay, so what we're going to do here is we're going to start from one data set, and then so the input will be a typical data set, and the output will be that transformed data set that we then will put into a statistical model. So the input here is I'm going to get you to, in the library section at the top, add tidyverse as well. And then add Palmer penguins right below it. Yeah, Palmer penguins. P like pen. Yeah, penguins. Perfect.
And so you have to. Package. Yeah.
Yes. And you just have to install that. Yay. And then load it up at line 4.
Yeah.
Great. Awesome. So the first thing that we want to do is just have a quick look at what the data looks like. So type out penguins, pipe. I guess you could do it another way, but penguins, pipe, enter, and then glimpse. And then run that. So you can see here, I think maybe we used this last time. I can't remember. But you can see here that there's a bunch of different variables. It's very basic, but it's also quite clear. For instance, there's the bill length in the units being millimeters, bill depth in millimeters, flipper length in millimeters, body mass in grams, then sex, year, and there's also the other factor variables being species and island. So there's probably a couple of research questions that you could ask here. We'll go over like a really basic one of, if you know what the body mass of the species is and you know what the sex of that species is, can you predict or can we estimate, I shouldn't say predict, can we estimate what the bill depth will be? It could also be bill length, but let's say bill depth. And so the way that we'd construct the model would be, so if you create a new line, right now we'll assign what we're going to do into an object, test underscore model. This is just going to be the first pass, the first test to.
What did you say? Like
test? Test, like test. Test.
Test.
Yes, underscore model, and then assign the assignment operator. Yeah, LM. Open close bracket, and then inside do bill underscore depth underscore tilde and body underscore mass underscore grams plus species plus sex, comma, data equals penguins. So if we run that, and then we want to just see a look at, inside, so we'll type out, go back to the script, and then type out tidy, open close brackets, tidy test, test model. Run that. Did you run tidy models at the top?
Probably not. I just install it.
There we go. There we go.
Yes.
Yes, there we go. Okay. So this is the output of that linear regression. And because our question was if we knew what the species and the sex was, as well as the body mass, what would be the estimated build depth? And so here we can see that the estimated build depth would be at least based on body mass index, body mass. The way that you interpret that estimate is that the body mass, 1 unit increase in body mass is 0.000706 increase in build depth, which is very tiny. And that's also kind of hard to interpret. So basically what that's saying is that for every 1 gram of increase, if we knew what the species was and if we knew what the sex was, like keeping them constant, then 1 gram increase would be 0.00076 increase in build depth, which is really like minuscule. It's so tiny. And so this, you might have noticed why, like that I focused on the estimate and not on the p-value. There's a whole rant that I have about p-values, but if you'll notice there that the p-value is actually very, I think it's quite significant, quote unquote, significant. It's a very small p-value. So if you were to go with the idea of the typical determining whether something is scientifically important or whatever, it would be based on p-value. But here we could see if you look at the estimate, even though the p-value is saying one thing, it's actually a really, really tiny estimate. So it's not really that meaningful. And there might be a small increase in build depth based on body mass, but it's not that much. But so the thing is that we also want to check to make sure that check some of the assumptions of the linear model. Not all statistical tests have these, but the linear model does have this. So if you type out plot and then type out test_model and then run that, you'll get a series of 4 plots. So I think you'll actually have to be inside of you have to hit return in the console. Go to the console and type out enter, or hit enter. So these are a series of tests. I'm not going to, I want you to, so hit it again. So
Okay.
The one that I think is a little bit easier to interpret is the QQ plot of the residuals. And more or less what you're looking for is something that is that all of those dots more or less are along the line. Now you can see here at the upper end that it kind of deviates a little bit from that line. And this is where we would start looking into why this is the case. Now, when you have a ton of models to run, let's say you're running doing a bunch of linear models on metabolites, which probably several of you have to do, you can't reasonably check all of the residuals for all of them. So you'd often do the transformations to deal with these issues within the model. But so let's go and create a new line. And I want to highlight maybe one of the reasons why this QQ plot is kind of deviating upwards. So if we type out ggplot, open close bracket, and then type out penguins, comma, aesthetic, or AES, open close bracket, x equals bill underscore depth. Could also be body mass index, but let's just do bill,
sorry.
Bill, yeah. Bill underscore depth underscore mm. And then go at the end and do plus at the very end. Plus, and a new line, geom underscore histogram. And then run that. Oh, we first have to... Oh, no, it works. Oh, no, you have to run it again. Yeah. So you'll kind of see here that it's a little bit of a bimodal, like potentially a bimodal distribution, meaning that there's two peaks. It kind of goes up at first, then it drops down, then it goes up again. So one of the things, variables do not need to be normally distributed when they enter statistical tests. This is often a confusion that, a misconception, I mean, that people have because unfortunately the stats education isn't always the best. It's hard when you have statisticians teaching non-statisticians stuff. But so the especially when it comes to the why of the model, the bill depth here is what we're interested in. Sometimes it's a little bit more sensitive to what the distribution is here. So the assumptions within the linear model are that the residuals are normally distributed. So that QQ plot is based on the residuals. Now, what residuals are it's the error term. It's the leftover of the like when it's the leftover from the linear model. So the linear model assumes that the residuals will be more or less around the line of best fit. And if they're not, then it could mean that you're not using the right model, or it could mean a number of different things. So maybe like if you have a data set that's an exponential growth, then you would see residuals that would be completely not normal because not normally distributed, because you're trying to fit a straight line to an exponential curve. So you'd have to do some transformations to change that exponential curve into a flat curve, which would, I think, often be a log transformation. Okay, so let's get to the transformation. So what we want to do is we want to actually transform all of these data into something that makes a little bit more sense. Now, like I said before, there are so many different ways of transforming data, and I'm going to show you just like a couple of the common ones. So let's type out penguins, type, a new line, recipe, open close bracket, bill underscore depth. Actually, here you can just copy and paste the formula from the linear model. Or actually, you can just, this might be fast too. So bill depth, yeah.
This one.
Except for the data, not the data, just from sex until bill depth, yeah. So here what you're saying is, okay, recipe, this is the model that I want to be running. So you're going to have the bill depth as the outcome variable, so the Y variable, the body mass index, species, and sex as predictors or as like the exposure variables. Then we pipe. So you have to pipe right before the comment. And then this is where you can start doing the transformation. So all transformations start with step underscore. So here we're going to do a log transformation, because commonly data are log transformed because it seems to help with the residuals a lot more. The side effect, unfortunately, is that interpreting the results is a lot more challenging, and I'm going to show that later on. But so every single step function, you also have to say what you want to log. So in this case, we want to log all number variables. So unfortunately, we would do all underscore double, because a double is also a number. It's a programming thing. And then do another pipe, and then we'll also do a normalization. So what exactly is a normalization? It is, so step normalize. So normalize is when you take a variable, you set it to be that the mean is 0, and that 1 unit increase is 1 standard deviation. So you'd have the mean being 0, and 1 unit up or down is 1 standard deviation up or down from 0. If you look at the results that we just showed, so one nice thing about using normalizations is that it makes the intercept a little bit easier to understand. So if you look in the model, on the model results, and it says intercept, so the estimate for the intercept is 15. What the intercept is saying is that when all the other values are set to 0, then the build depth will be 15.2. Now, can you kind of guess, is it possible that body mass can be 0? No, not really. A body mass of 0 would mean that you don't exist. So and in this case, a 0 for sex would be, I believe, female here in this case, and 0 for species would be the other species that isn't shown here. I can't remember which the other species is. But so it would be if the species is female, if the sex is female and the species is the other one, and the body mass is 0, which is not possible, then the build depth would be 15. So that's how you would interpret that. That's not really that nice to interpret. So if we normalize the data, that means that now the mean is 0. So then when you interpret that, the estimate will change, and it'll be when body mass is the average, then the intercept will be, then the build depth will be something. So that's kind of how you interpret why you might normalize data, is because it helps with interpretation of the model. So like we did with the step log, we also have to do it with the in there. So we could do all double, but it will make interpretation a little bit more difficult. I'm just thinking, I guess it wouldn't make it too much more challenging. No, let's do all underscore numeric underscore predictors, just so we show the difference here. So here you're saying apply the transformation to all the numeric predictors, which would be only body mass right now. There's other ways of doing some transformations that are not just that are also for the what's it called? The categorical ones. But there's a lot more transformations for numeric data than there is for categorical. But yeah, so now what we want to do is eventually use this in the model like we did above. So I want you to pipe to prep. So pipe.
Yep. Wait. Sorry.
I think you have to hit enter. Yeah.
Yeah.
And then prep.
Mm-hmm.
So it's a little. I don't quite understand why there. Well, no. I guess there's a couple of reasons why you have to do this twice. But you do prep first so that you tell recipes to calculate all of the stats. So, for instance, in order for you to do the normalization, you first have to calculate the mean and calculate the standard deviation in order to then do the normalization. So that's what prep does right here. There's also other transformations that need some calculations to be done first. So this is what prep is doing. Then we're going to pipe to a thing called bake. It's a little silly, bake recipes. Now, the reason why you have to do prep and then bake is that if you did some like a little bit more fancier splitting the data into a training set and a testing set, like for instance, if you're doing some predictions or if you're doing some machine learning type things, then you'd need to do a splitting the data in a training set and a testing set. But in this case, we don't really need to. But if you did need to do that, what you do is you do bake, and then you'd apply the bake to the whichever training data set that you're using, or it might be the testing data set or whatever it is. But in this case, we don't want that. So what we have to do is we have to say new underscore data. So inside of new underscore data equals null. So you're saying just use the original data above. All caps, null, N-U-L-L.
Yes. No.
Yeah.
Okay.
And then pipe, and then run this.
And then I run the whole thing?
Yes, and then you run the whole thing. So now what you can kind of see here is that the body mass and the build depth they look more. Yeah, so so you can see here the body mass, there's negative, which isn't possible, but that's because we normalize the data. So now a negative value means that it's below the average, and a positive value means that it's above the average. So it would be 1 unit increase above or below. But with the build depth, it doesn't do that. So what I want you to do now is go to line 23.
Mm-hmm.
And I want you to create a new object called transformed penguins. It's like Transformers.
I think I wrote it wrong.
Penguins, and then assign from penguins. So then you run this. And then now what I want you to do is go copy and paste the linear model that you had calculated, that you had done before on line 17.
Mm-hmm.
Line 17 above. The whole line.
The whole thing?
The whole thing. The whole line.
Yeah.
Not just that, but the whole line.
Sorry.
Yeah, no problem. Yeah. And then copy, and then paste down below. And then replace the transformed, penguins with transformed penguins. And then the test model with the transformed model. And then run that. And like you did above, you do tidy underscore transformed model. Oh, did you run? Oh, there it is. Yeah. So let's run that first. Yeah. So now if we look at the estimates from here, we can see that the estimate has changed. So because the values are now log transformed and the value is for every one increase, a unit increase is a standard deviation. Don't remember how you'd exactly interpret this, but it has something to do with it's a percentage. So for every 1 unit increase, it's a percent increase in the other thing. I can't remember. But this is something that you have to look into and learn, because each transformation will change change how you interpret the results, depending on what transformations you do. Now, sometimes that isn't important. Like if you're asking a very specific question like ours, then how you interpret the estimate is important. But sometimes when you're running a bunch of things, what you're looking for is what of everything that you're doing, what of everything that you're running has a bigger impact on the variables that you're interested in compared to the other ones. So it's more of a comparison. So this is why normalization is also really useful, because it's easier to compare, because all the units are on a 0 to 1 scale. So it's easier to compare the values of the estimates of those, because you can say for every 1 increase in the unit, it leads to an X increase in the outcome variable or the Y variable. So then you can see that across all the different models that you run, it's the same interpretation. So normalization is actually a really, really nice way of standardizing not just the variables that are entering the model, but also the estimates that are coming out of the model. The log transforming can be really useful if you want to interpret based on whether the estimate will be a percent increase. So I believe that if we would change you don't have to do this, but if we were to change the step log to all outcome, I believe it would be all numeric outcomes, then the interpretation would be for every 1 unit increase in body mass index is a X% increase in the build depth length. Build depth millimeters. But maybe we can try. Let's see. All underscore.
Here?
Yeah, at the log. Yeah. All underscore numeric. No. Delete. And instead do all underscore outcome, maybe. All underscore.
Outcomes?
Yeah, I guess that works. Yeah. And then close, and then run that. And then run the model again and run the tidy output. Yeah, there we go. It didn't really change. Basically the same, right? Yeah.
Yep.
Oh, I wonder if that's because it does that automatically. Like it doesn't log transform the outcome. Interesting. So then I think actually in this case, then the interpretation would be a 1 standard deviation increase would lead to a 0.03% increase in build depth length, which is very tiny. So you'd have to get a lot of weight in order to make any meaningful change in build depth length. It might actually be 3% because you might have to times it by 100 in the end. But so anyway, the other nice thing too is that again, the intercept here, we can interpret the intercept as the mean. This would be the mean build depth length, assuming the average weight and the sex being male, sex being female. So that's kind of the nice interpretation bit. We can even now do the plot at the end. And then transformed model. Run that, and then you'll have to hit enter each time, unfortunately. in the console, yeah. Enter one more time. So here you can see now that it's a lot flatter than before. So the ending point, before it was kind of like curving upwards, and now it's kind of like flatter. So you can say, then we kind of know. So if you hit enter again, and then hit enter again, one more time. Yeah, so these things, like these, in general, you want to see that they're kind of around each of these lines, like they're equally around the lines, and not too far. So this like leverage and residuals. So leverage meaning like how much influence these data points have on the model. It says 115 there and 293. So 115 is row 115 and 293. So those would have potentially a bigger impact on the estimates than some of the other variables do, some of the other rows do. So this kind of tells you what to look for when you're looking in your data. It's like maybe these might be just really big penguins or something, or just like they might have really long or really deep bills. What is bill depth? Oh, maybe it's like really wide. I don't know. But anyway, so that would just be an indication of what to look for in your models. There's several other like transformations. I think the two that I'm going to get you to add are fairly common, I think, to several fields. The first one is correlation within the predictor variables. So one of the assumptions of linear regression is that the variables in the predictor side are not highly correlated with one another, because one of the assumptions is that they are independent of each other. But if they aren't independent, so for instance, let's say you put in what's something that's really dependent on each other? Height and weight in humans. In general, if you're taller, you're going to be heavier. So those are really highly correlated variables, and you don't want to include those into the model because they might introduce some bias, because what it's actually saying is what you're trying to then estimate is based on data that's already highly correlated. So you don't want variables that are highly correlated with each other. And one way of dealing with that is doing a transformation to remove some of that correlation, or to remove some of the variables from the correlation. And remove some of the variables from the model. So you do this thing called step. So we can create a new line below line 26.
Mm-hmm.
And do step underscore core. And then do all underscore numeric underscore predictors. And then we pipe at the end. So then what that will do is that it'll say, okay, are there any variables that are highly correlated with each other? If there are, I think they might might remove the variables from them, or do some transformation of those variables so that they aren't correlated anymore. Another really common transformation or issue is a thing called non-zero variance. So non-zero variance is when you have some variables or some data that are either that have a lot of missing, or more likely where the values are very similar. So sometimes this happens with the way that data is collected, or maybe it was like some issue with like the machine, or there's many different reasons for why data might be like this. But like, let's say you measured height. Here's a good example. Maybe is you measure height in the army from like army recruits. But most militaries, I think around the world, most militaries have a height requirement. So the values are going to be very similar with each other because they're all going to be mostly the same height. So when you're measuring them, you're going to have a column of height values that are all going to be 170, 175, 174, like really, really similar. So when you do some modeling, then you're going to have an issue because there's just going to be a lot of the same stuff. What's going to end up happening is that the data is going to look like there's not going to be a lot of unique values. So that's what non-zero variance is where there's not a lot of unique values. And you can deal with this and I think actually sometimes you deal with this with some omics type data sets, especially the way that the data is measured. But so the way that you deal with this is add a transformation so you'd add another step function.
Coming.
Yeah, no problem. Step underscore NVC. NZV, non-zero variance. And then you do all doubles or all numeric predictors. And then pipe at the end. This doesn't apply to things like integers because integers are treated differently inside of models. They can have a lot of similar values, and oftentimes they might be converted anyway into like some type of categorical variable. That's what integers might end up becoming. Same thing with.
I have a question.
Yes.
So what does the step core like exactly do? Does it step core and step NZV exactly do? Does they remove the correlated variables or do some transformation?
I believe. Let me just quickly check. I believe they might drop the variables. Yes, they will. NZV will remove variables.
The near zero variance.
Yeah, the near zero variance. Because the thing is, like, if you're having a variable that has a bunch of that has very few unique values, it's either A, not useful data, or B, something was wrong with the data collection. So from a statistical point of view, you don't want to keep that anyway. So you drop it because it's not usable. Like you can't do anything with that type of data because it's like you could maybe beforehand, if it was a really important variable and you know that it was actually just coded incorrectly as being numeric when it should actually be a factor variable, then you could say, okay, convert this, like if we're talking about the height in the army, convert this height in the army to a factor variable where then it's treated as people who are 170, 171, so 172, 173, and so on. But then, yeah, it gets a little bit tricky there. You could actually maybe convert that into a numeric, into an integer, and that might actually be fine.
And can I also ask, like,
yep.
Does the order matters? Like, should these non-zero variance should be before we do the other transformations, or this is created after the normalization happens?
No, this is a really great question. There's actually on the recipes website, there is practical advice, a page called Ordering of Steps. And so they give you a recommended list of how to do it. So one of the first things is you first impute If you're going to be doing any imputing, then you do imputation. Then you do handling of factor levels. Then you do transformations. Then you discretize. Like, for instance, if you want to keep some value that has non-standard, non-zero variance, then you maybe convert that into a something that can be usable. Create interactions, then normalizations, then either more complex transformations. But again, it's on the website, on the recipes website, that has this list of how to, like, what are the steps to take. So strongly recommend looking in that list there.
Okay.
It's in the articles section. There's, like, at the top part says articles, then you click more articles and it'll list there. And then the core, the step core is, I think you can run, let me just check here. It also removes variables. Yeah. So both those remove variables, because again, you don't want to include, so you all know what body mass index is, right? So the reason, who doesn't know what body mass index is? Okay, great. So body mass index was actually created because of this issue where they needed to run, like, they needed to be able to assess a person's weight given their height, because we know that weight has strong effects on lots of health outcomes across, like, a bunch of different diseases. Either low weight or high weight. So very low weight, very high weight, those all have effects on health. What they ended up the reason why they created the body mass index is because weight and height are so highly correlated that you can't include them in models, even though they're really important. So what you have to do is you have to create a second variable that takes both of them into account. And there was a lot of development many years ago into what is the best way of determining, what is the best index for calculating, for taking into account both weight and height. And they ended up coming on to body mass index, even though personally I think it's not maybe the most intuitive for the best measure, but it seems to be useful in many ways. So that's one way of dealing with highly correlated variables, is by saying, making an intermediate variable beforehand and then removing those other two variables. So, but that would be potentially something you do beforehand, because you already know this, but not always do you know this. Sometimes you have this data set that has, several hundred variables, and you need to be running models on all of them. And you don't necessarily have the time to be able to dig into each individual, like how each individual variable correlates with one another. And so it might just be easier to drop the ones that are highly correlated with each other. But I hope that answers your question.
Can I ask another question?
Yes, please.
Can you remind me again what does the PREP and the bake do?
Yes, yeah. So what PREP does is it says it'll, because what you want to be doing is what you might want to do is determine some of the standard, like, for instance, the normalization, like, let's say the normalization, that calculates some stats in order to, some really basic stats, mean, standard deviation. And what PREP does is it says, okay, all of these transformation steps, all of these other steps above, convert them into some type of, like, formal specification that then we can use on the data set. So you're saying, take this recipe now and apply it to the data. That's basically what prep is saying. Then what bake is doing is you're saying, okay, now you have the specification of the types of transformations that you want to be doing. Now apply it to that data.
Sometimes penguins, right?
Yes, but sometimes you want to apply it to the test data set rather than the training data set. And this is a way of like testing to see whether or not the transformation even works in another data set. So this, if you're not doing machine learning or if you're not doing prediction, these two steps are necessary, but they're not, what's the right word? They don't affect you. You don't have to know anything about them aside from you need to run prep and you need to run bake with data, new underscore data equals null. But if you are doing prediction and if you are doing machine learning, then you do need to know how to use these recipes with your testing data set and not just your training data set. Because with prediction, unfortunately, again, this is another, like p-values, this is another thing that people often use as a word, and even here we see all numeric predictors. To predict, anybody can predict anything. This is going to be a little bit of a rant, but anybody can predict anything. What makes it important is whether or not that prediction is true or not. And in order for you to determine whether the prediction is true or not, you have to test your prediction on new data and assess whether or not that new data also has the same prediction. So if like a lot of us, if you have the same data set and you run a statistical test and you get estimates from the end, you are not doing prediction because you're not using new data. You're saying we're estimating the effect of body mass index on build length, on build depth. But if you were to say, I want to predict the effect of body mass on build depth, then you'd say, I'm going to collect body mass from a bunch of penguins, and I'm going to estimate from that new set of data, going to estimate their build depth. And if that estimation is the same as then your calculated estimation, your prediction is accurate. So it's a little bit like the weather. You know, you go on the weather forecast and it says, today is going to be sunny and no rain. That's a prediction, right? That's the prediction, is it's going to be sunny and no rain. But then when the day ends, it was actually cloudy and rainy, the prediction is false. So you've collected new data because now you have had that whole day pass, and now you know that it was not, the prediction was false. But so then what you can then do is you can use that information in later modeling. So you can say, okay, so now we know that prediction was false. So we'll use that new data that we've just collected and we'll try to improve our prediction for next time. Another day passes and you say it's going to be cloudy with no rain, and it ends up being cloudy with some rain. So then you're a little bit better at being predicting. So prediction always depends on new data. You always need to have new data in order for you to talk about prediction.
So what would be so let's say if you put a new data here in the bake, what would be the transformed penguins in the end, the output?
So in this case, what you do if you wanted to use the new data, not null, you'd have to create a new object at the very beginning called test underscore penguins and training underscore penguins. And you split the data into two. So normally it's like you split the data. There's another package that does this called R samples. And what you do then is you take about 80% of the data for your training. So you run your transformations, you run your models on that data, and then you take the output, then you take that model and you use that to apply it to the testing data set, which would be about 20% of the Penguins data set. And so here, that's where you'd say, instead of bake new underscore data equals null, you'd say new underscore data equals test penguins, not train penguins. It's a small, like, yeah, if you want to learn more, the website does go over this in quite a good amount of detail. And the Tidy Models also has their own website that goes into some of this in a little bit more detail. But yeah, the new data is when you'd use either the test penguins or the training penguins. Do you have any other questions? Does that make sense? Maybe it doesn't make sense right now, and that's also okay.
So the prep
stats is hard.
So the prep is, if I split the data, I use prep for training data, and bake, I will just change it the null if I have a test data from that data split.
Exactly. Yes. Okay. You'd prep on the training data and you'd bake on the test data.
Does I always need to write prep and bake? Or if I remove those, will the recipe still work?
You need those two steps.
Okay.
If you're going to use this outside of the Tidy Model framework, but if you use this within the Tidy Model framework, you actually don't even need to do prep and bake. You can say what Tidy Models allows you to do is you say, okay, here's the recipe. You set the model that you want. Then you say, here's the model. Here's the formula. Now do run everything all together. And it takes care of everything for you. So it's really, it takes a little bit of time to understand the basic design, but it's a quite powerful approach to doing things. You're more or less separating out each of the individual steps and then merging them together all at once. So in the Tidy Model setting, you don't need to do prep and you don't need to do bake. But if you're not using the Tidy Models framework, then you do need to do prep and you do need to do bake.
Okay.
Well, that went a little bit over time.
Yeah. I have another question.
Great questions. Yes, we there. I have. Go ahead.
Like here, for example, like we were doing one model, right? And then we were able kind of like to visualize the QQ plot and all of that. But if we're working like, for example, like metabolites, and then you have like to do a model for every metabolite, and then you have like, I don't know, 7,000, 9,000 metabolites. Is there like an easy way to do like visual inspection or what is the best way to transform all the data?
I think if you have a bunch of, the advantage of doing like some proteomic or like metabolomic type data is that it's all going to be numeric and it's all going to be more or less, I think, the same. You can make a lot of similar assumptions about the data because it's all similar underlying processes. You're calculating proteins or whatever inside the blood. So like they're all biological is what I'm trying to say. They're all biological measures. So in that case, I would not try to do like check assumptions on each of the models. I would say transform all of them to the same things like normalization, log transformation, whatever you decide as being an appropriate thing to do, and then run them all at once with those standard transformations. Then at least that way you're able to compare because in this case the statistical test is more more about the comparison between variables, the comparison between the metabolites rather than the specific metabolite itself.
Yeah.
So that's when like the standardization allows you to be able to compare a little bit better than others. So I hope that makes sense.
Yes.
Yeah. Great.
Thank you.
Yes. Cool. Okay. Well, thank you all very much. And I think in early November, maybe in a month from now, or we could do close to end of November so that we slowly get back to the beginning of the month. So maybe November 27th. Would that work for everybody else?